Have you ever heard of Euler's constant? Yeah, it's around 2.7. No, I'm talking about Euler's constant. Here I have graphed the harmonic series as a set of boxes as well as the curve 1 over x. As you can see, our series is bounded below by the integral of 1 over x from 1 to infinity, but there is this little difference between the areas, and that's what Euler's constant is, also known as the Euler-Mascheroni constant. Numerically, the constant is defined like this. We take the negative log of n, which is the negative area under 1 over x, and then add it to the partial sum of 1 over k. And then we take the limit as n approaches infinity to get the total area. But here's a good question. How do we know this area is going to converge? Define a sequence gamma n, such the limit as n approaches infinity of gamma n will just be Euler's constant. If we can show this sequence is monotone decreasing and bounded below, then by monotone convergence theorem, we know that it converges. When we take the difference of gamma of n plus 1 and gamma n, we get this, which we can quickly simplify to something that looks like this. And if I was more motivated, I'd prove this, but it's actually always negative for any value of n. Therefore, for any n, gamma of n plus 1 is less than gamma of n, so gamma n is strictly decreasing. Now to bound our sequence, we know that the series 1 over k will be bounded below by this integral, and trivially log of n plus 1 is going to be bounded below by log of n. We can then take this log n and subtract it on both sides, which will get us this inequality. The sum minus the log is greater than 0. Thus, we've shown that gamma n is bounded below. Therefore, by monotone convergence theorem, we know that our sequence converges to a real number, and that the Euler-Mascheroni constant is well defined and non-convergent. Thank you for watching. Also, what is this constant used for? Well, we're going to get into that later.